Our very last section of the semester here is on a special kind of graph called a tree graph, where a tree graph is a connected graph with no circuits, no cycles, no loops, none of that sort of thing, where they get the name tree because, well, if you look at the arrangement of a tree graph, it can be seen sometimes as looking a bit like a, well, tree, just with nodes and edges instead of roots and branches. And yeah, there's a little bit more we can develop with that notation. We're not going to see too much of that in this class. For another example of a diagram that can be thought of in this context is something like a family tree, where you could usually represent a family tree as a tree graph, except in certain cases where I suppose you may be more interested in the purity of the royal bloodline than you are in avoiding whatever happened to this jaw here. Is making fun of the Habsburg jaw ableist? Maybe. Anyway, what we're looking at here, as we see, are these kinds of graphs where we have three properties that come as a result of this construction. That we must have, there is only one path, there's one and only one path between any pair of vertices. Then we have to have that every edge is a bridge. If you remove any one edge, you'll end up with two components. And then if you have n vertices, you must have n minus 1 edges. So for a couple of quick examples here of how you can make something that isn't a tree into a tree, we can look at these graphs here, where in that first case there are actually a few different ways we can tree this one out, but in particular if we remove the edge BG, then we would end up with sort of a curved around path there from A down to G, and paths are actually trees. They're very simple trees. Not very tree-like, they're more like logs, I suppose, but they are considered for our purposes trees. Similarly, in that second case, if we remove the edge BC, then we would end up with the star graph in that case, where the star is also a kind of a tree, which is kind of a little weird, but this is what happens with math notation. You end up being a little more generic. Maybe we want to be something that sounds like a cool name. And then for our last one, that does look a bit more tree-like there. If we remove edge CF, or for that matter, we could have removed BF, either would have served the purpose there to remove that circuit and thereby result in a tree graph. And for another example, we can talk about here, for another example of whether things are or are not trees, we can consider these three as well, where in that first case, we would not have a tree because we do not have a connected graph. Technically speaking though, those null graphs that we have out there are trees themselves. So we do have a special notation for something like this. We have a group of components that are all trees. We call that a forest, but we're not going to worry too much about forests in this class. Then in that second case, we've got another one of those things where it's actually a path that just has been jagged, made a bit more jagged, jaggedified. I don't know if that's really a word, but point is that would be a tree because we have that everything in there is a bridge. We have no circuits, and for our 5 vertices, we've got 4 edges. And then finally, in the last case, we've got something very, very similar, but because of that extra edge, we end up with a circuit. So that third one, even though it looks like it could be made into a tree, and it could be made into a tree fairly easily, in this case, due to the circuit, it is not. And there are a lot of combinatorial properties you can do with things in this rough pattern with the idea of a tree graph, but the big thing we're going to focus on in this section is more of an application for trees in terms of a thing called a spanning tree for a given graph.